Okay, I will now go through the second question in the SHM test, which was about this pendulum. So Hannah is skiing at Treble Cone. She sits on a chairlift and it swings back and forth with a period of 3 seconds. So here's T and an amplitude of 1 meter. So that's A. Hannah realizes that she is part of a pendulum. On a diagram above, mark the position along the dotted line where the chair experiences maximum positive acceleration and maximum positive velocity. So at this point, she will be experiencing the maximum positive velocity as she's swinging forward. At that point, she would also be experiencing the maximum negative velocity as she's swinging back, but that was the correct point to mark for maximum velocity. At this point, she'll be experiencing maximum positive acceleration. And the reason for that is that when her displacement is max negative, which is here, which is at this point, that's when her acceleration will be max positive. So it has to be at this side, not at that side. Okay, so that wasn't achieved. Calculate the effective length of the pendulum. Write your answer with the correct number of significant figures. Okay, so here we have to use the fact that T is equal to 2 pi root L over G. And then we want to get L out of this. So we want to rearrange this for L. So the first thing we do is we divide both sides by 2 pi. And then we take the square of both sides. So we get T squared over 4 pi squared is equal to L over G. And then the last step is that we multiply both sides by G, and we get T squared G over 4 pi squared is equal to L, which will be equal to, well, we were told that the period was 3 seconds, was it? Yep. So we're going to get 3 squared times 9.8 divided by 4 times pi squared. So let's do that. So it's 3 squared times 9.8 divided by, and now it's the denominator, so we need to put a bracket here, 4 times pi squared, and then close bracket, and equals. So it's 2.23 meters. Calculate the pendulum's velocity 0.5 seconds after it passes through the midpoint, moving to the right. So after it passes through the midpoint, if it's passing through the midpoint moving to the right, we're going to use the set of equations for which the displacement is described by a sine function, right? So we're going to have y is equal to a sine omega t, but we're wanting the velocity in that set of equations. So for that set of equations, the velocity is equal to a omega cos of omega t. Okay, and then we substitute in the values. So we had an amplitude, was it 1 meter? I think it was 1 meter, yep. So we have V is equal to 1 times, and we had the time period, so, and we want omega, so we were going to go 2 pi over the time period, which is omega, right? So 2 pi over 3 times the cosine of, and here we have omega again, which is 2 pi over 3 times the time, which we're given here, which is 0.5. Okay, now in this one, it is important that we do it in radians, because this angle here that's inside here is not in degrees. It's clearly not in degrees. It's expressed in terms of pi. Okay, and so, whoops, that's what we want. We don't want this. Cancel that. Okay, and so let's do this calculation. So it's 2 pi over 3 over 5 is okay. So 1 times 2 times pi divided by 3 times, and now this calculator makes me do things in a very reverse order. So I'll do it over here. I have to do what's in the bracket first and then hit cosine. So I'll go open bracket 2 times pi divided by 3 times 0.5 close bracket cosine. Okay, equals. And we get 2.09 or 2.1. Assuming that was in radians. It's in degrees, so let's change that to radians and do that again. So this was a mistake that many of you guys made, and it's a mistake that I made as well. So let's do that again. What was it was 1 times 2 pi over 3. So it's 1 times 2 times pi divided by 3 times 2 times pi divided by 3 times 0.5 close bracket, and then we take the cosine of that, and then we put equals, and we get 1.047. 1.05, I'll say, meters per second. Okay. Holly suddenly appears. That should be Hannah. She swings her legs, making the pendulum resonate. Explain what resonate means. So we can say it in terms of the pendulum first. So, or we can say it in general first. So resonance is when amplitude reaches a maximum at a very precise driving frequency. And in this particular case, and this would have been sufficient for merit here, it is when the swinging legs frequency matches the frequency, sorry, it should be the natural frequency. Let's just rub that out. The natural frequency of the pendulum or the swinging chairlift. So when she's forcing or driving the pendulum by swinging her legs, when that driving frequency is the same as the natural frequency of the original pendulum, then it will resonate. Okay, she sees a sign that tells her not to swing in the chair and immediately stops swinging her legs. On the first set of axes below is a graph of displacement against time for actually 4 full oscillations while she was swinging her legs. So she'd reached this maximum amplitude and the amplitude remained constant. On the second set of axes, draw a graph of the displacement against time for 4 full oscillations after she stops swinging her legs. Okay, so if she stops suddenly swinging her legs, then the amplitude is going to die down because of friction. Right? It's going to have the same period as the original swing, but the amplitude is going to decrease. Okay, so the easiest way to draw this is to first draw the decay envelope, which should be exponential, and you need to show that it's exponential. So it's going to look something like this. And the same on the other side. And then draw in the 4 oscillations. So if we go like this, and then we can maybe even say that, because we haven't drawn it very precisely, this is exponential. Decay, maybe. Okay. Finally, draw vector diagrams and use them to explain how the period of the pendulum's oscillation would change if the pendulum was longer. So here we'll draw the short pendulum. In fact, I'm going to make it a bit more extreme. Then I'm going to draw a longer pendulum with the same displacement. And I'm going to draw in those theta. So we have a weight force here, and we have a tension force here. We have a weight force here, and we have a tension force here. And if we add those up in a vector diagram for each of them, here we have the weight force, and here we have the tension force, and the net force is going to be quite large. So that's the restoring force, R1. This is the weight, and that's the tension. And in this instance, we have a weight force, and we have a restoring force. And we have, in fact, I'm just going to make this a little bit more similar to the previous diagram, similar in size. In the second situation, we have the same weight force, but because the angle of the string is smaller, we're going to have a tension force that looks more like that. And so this is going to be R2. So this is the weight, and this is the tension in the second situation. So, and I'll number these diagrams so I can refer to them, 1 and 2. So, with the short pendulum, as shown in 1, the restoring force is big for a given displacement. And that's because the horizontal component of the tension as horizontal component of tension is big. Hence, A is bigger. Oops. I might just move it down a bit like this. A is, I just can't draw on that part of the diagram. Right. Let me just fix it. I'll move it somewhere else. Hence A is, oops. Is big. And T, the period, is small. And so that, because this component here, of this horizontal component of the tension force, is big for a short pendulum because of that big angle, we're going to get a big restoring force, therefore a big acceleration, therefore a shorter time. And we can say then conversely, in 2, the longer pendulum is at a smaller angle for the same displacement. So restoring force is smaller, leading to a longer period. There's probably a more efficient way to explain that, but that's basically it. So because, have I got something like a laser? Oh, I'll just use a cursor. So because the, oops, that moved the whole thing. Because the angle here is big, because the pendulum is small, even though the displacement is the same in both cases, the restoring force here will be bigger because the tension is acting at a sharper angle. That's the basic argument for how you can explain why the shorter pendulum will have a shorter period. Okay, so that's it for the test. I hope that all makes sense. If you still have questions, just